All right. Hello, hello. Who's here for BitVM? It's not BitVM. Sorry, you're out of luck. So I'll be talking about BOLT12, which is nothing to do with scripts really, although there'll be some hashing involved. This is more of a lightning talk. So maybe just show of hands first. Who's familiar with BOLT12? Got quite a few actually. All right. So I'm going to kind of go through some of the background of where we came from and why BOLT12 is important. And then I'm going to dive into some of the technical details. And during that phase of the talk, I would love if you guys kind of make it a little more interactive. And so I'm going to kind of just go through, kind of do a little deeper dive into it than probably what you've seen before. All right. So here we go. So let's talk about cash and its important qualities. So someone could hand over a $20 bill to purchase something at a store, and they don't need to fill out any paperwork or be worried about transactions not going through. There's no third party involved. The transaction is private and secure. As the world has transitioned to digital money, those essential properties have been lost, however. A lot of people have not recognized this now, but they will in the future. Bitcoin was invented to solve these problems, and along came Lightning to improve Bitcoin's ability to be used in instant payments. So let's look how Lightning is done today. All right. So BOLT11, I think a lot of people are probably familiar with BOLT11. This is the predominant protocol for making Lightning payments today. It certainly gets the job done. It's ubiquitous. It's in every wallet. Supports BOLT11. But there are a number of drawbacks to BOLT11. So it's pretty optimized for a select use case, a customer paying a merchant. It's invoice-based, enabling one-time payments that do not allow reusable payment IDs. So an invoice cannot be reused, for instance, and there's no human-readable names like you might get in like a Cash App or a Venmo, right? So those were some drawbacks to BOLT11, and along came LNURL. So LNURL solves several problems. Most fundamentally introduced the notion of a web server to issue invoices. So you can get a reusable payment identifier this way because of the reliance on a server that can issue a new invoice each time someone wants to pay you. This is great for tips or donations, for instance. You get a QR code, and there's also like LN address, or Lightning address, which has human readable names. So these are all innovations on top of BOLT11. So LNURL really advanced usability tremendously. However, if we don't advance the current solution, we sort of erode some of the core principles or properties or components of the Bitcoin, one of which is censorship resistance. So by law, servers cannot allow payments from certain jurisdictions in the world. There are privacy concerns, of course, as well. Servers learn who is paying who, the amount, and log all this that information. Even if a company has no ill intentions, it's still a honeypot of information for governments or hackers, and so that's pretty relevant today if you've been following the news. There's also some security concerns with LNURL. Servers issue invoices on behalf of the user, but there's nothing stopping from that server from issuing an invoice that pays someone else, itself, for instance, especially if the server's a third party, which is kind of pretty prevalent today with usage of LNURL. Or it could just be somewhat surreptitiously where maybe 1 out of every 100 payments is paid to someone else. So you might not even notice like you're missing payments. You could avoid detection basically. Yes, exactly. So along comes now BOLT12. So Rusty, I'm not sure if he's in the audience, but Russell proposed BOLT12 a number of years back. And this is kind of like bringing back some of these properties that we all know and love about Bitcoin, but unfortunately have been kind of eroded in the sake of usability. So now we're here to do it sort of in a manner that still has superior privacy, censorship resistance, and improved security. All right, so let's get into BOLT12. So this is where the more technical part of the talk starts. There's a lot of visuals here, and so hopefully it's not too complicated. And if there's any questions, please feel free to shoot a hand up or shout out. All right, so I'm calling this life of an offer. So what is an offer? An offer is like a reusable payment code in the BOLT12 world. You could think of it as like a precursor to an invoice. So here we have Alice wants to pay Bob for something. Maybe it's a donation, maybe it's for goods. Not really sure at this point. And Bob has an offer. So Bob has constructed this offer in such a way that he's able to receive payments in a pretty secure and privacy-focused way. The offer is communicated just like a BOLT11 invoice typically is. It's out of band, meaning not on the Lightning Network. So it could be through a text message, it could be in a tweet, it could be an email, it could be just in a QR code that you scan. And one of the things about offers is that they contain something which is sort of annotated on that picture there. It's a blinded path. So it's a way for Alice to basically contact Bob for an invoice without actually knowing Bob's node ID. So if you're familiar with Lightning, if you announce your node, your node has a pub key associated with it. We call a node ID. And if you have a publicly or known node ID and you're being paid, to that node ID, payments can be correlated to you, basically. Everyone or an observer, I should say, may be able to see who's paying you. So Lightning has today has great sender privacy, but not great receiver privacy. So BOLT12 aims to I guess fix that. Yes. So there's no limit, but there's a restriction in your QR code. So if you're using a QR code to communicate the offer to someone, then if their camera and their phone, for instance, isn't good enough to scan it if it's a huge size. Exactly. Yes, exactly. But you could use text message. You could tweet about it. Even the specification of offers gives a way to concatenate parts of an offer together using, I think, a plus sign. So if you want to break it across a bunch of tweets and you have a donation address. But yeah, we'll get into the blinded paths in a bit, but there are some more concerns about the availability of blinded paths as time goes on, because these are long-lived offers, or they can be long-lived. All right. Another thing that I'll get into, but offers may be denominated both either in Bitcoin and MSATs or in a fiat currency. And who thinks, or I guess, what's the reason why we would denominate an offer in fiat, for instance? Anyone have an idea? Merchants might want to, but why would they want to, right? Exactly. Yeah, fluctuations in price of Bitcoin, especially if these offers are something maybe they're weak, the expiration's in a week. Yeah, exactly. And so the offer the offer may be denominated in fiat, the payment will always be in Bitcoin. So we'll get into that. Another reason why you may want to do this is that it's kind of related, but an extension to BOLT12, which will happen hopefully in the future, is subscriptions or reoccurring payments. And such, like if you have a subscription to Netflix, they might denominate in a certain amount in fiat, but you'll pay them every month in MSATs or Bitcoin. Yes? Yeah. It was part of the original spec, but it was we kind of, I guess, we took it out initially just because it was a lot to implement, essentially. So, yeah, it was scaled back a bit, but it's still on the roadmap, and I'm sure Rusty would love to talk to you more about that at some point. But yeah, it's pretty exciting to have I guess as we go into this, we'll look at the format of the offer and how it can be extended too. So yeah, it's not like a one-time deal. It's, BOLT12 is done, but it could be extended just like the rest of the Lightning Network has ways to extend itself with features. All right, so I think everyone understands that one. Bob has given Alice a QR code in some manner out of band. And so let's dive into the QR code. So it's encoding a BEC32 string basically here. And it is very similar to what you would see for like BOLT11, only one difference you can see, it starts with an L and O, and that signifies this is an offer. There is a separator character, and then the actual offer TLV stream. So a couple things to note: there's no checksum like most BEC32 strings, and we'll see why in a bit. And not really represented here yet, but it is. It's not signed, and we'll get into that as well as why that is not the case. And while BOLT11 invoices are signed, BOLT12 offers are not. And of course, like I mentioned, it contains a TLV stream. So let's see what a TLV stream is. So if anyone's worked with Lightning, you're probably already familiar with this, but TLV stands for type length value. It's a way to encode data where the type is a number. It basically is describing what the type is, so that kind of maps to something in the spec. So for instance, the amount might be a type. The length of this TLV record would be the number of bytes in it, and then the value is those number of bytes essentially that follow it. So as you're parsing a TLV stream, which is a sequence of these TLV records, you would pull out the type, figure out how much of the stream to read, and then parse it based on that type that was identified. So it's pretty straightforward. And so I'm not going to go too much into the detail here, but that's what a TLV stream is, and that's how offers and other messages within offers are encoded. All right, so I can't see this very well, so I'm going to be looking over once in a while here. So here's the offer TLV stream. So on the left side, what you see is, if you're a programmer, it's equivalent to like a class or a struct in the language. It's identifying basically the different fields within it. So each row in that table on the left are the fields in this like class or struct. We're calling them records though. And on the right side, it's an instance of that particular class, if you will. So here we have an offer. It could have a bunch of different fields. There's chains, so this is like mainnet, testnet, etc. There's some metadata, which we'll go into in some later slides. The currency, if you want to denominate it in a particular currency. The amount, and the amount is optional, so if you want to have a donation address, you don't need the amount there. Feature bits are for extensions. We have an expiration, so when the offer is no longer valid, you will no longer get an invoice back if that time has passed. We have the blinded paths there, which I talked about earlier, and we'll jump into soon. And then some more informational fields, so like the issuer, if you want to kind of identify yourself with like a more human-readable string. Quantity is something it's in the offer spec now, but might not be as super useful to a lot of people, but you could specify the maximum number of items to purchase. So for instance, if this offer was for a cup of coffee and the max was 10, you could order up to 10 cups of coffee. Maybe it's not the most great example, but you could kind of think in the future when you think about like picking up items from a store and like scanning items on the checkout, like you buy some produce, you might enter like a quantity, so that could be useful there. But yeah, we won't talk too much about that. And then the last thing there is the node ID, and this is a potentially transient identifier, so it doesn't have to be reused. Basically, you could pick your own node ID essentially, as long as you have the signing or the private key associated with it. So we'll jump into that in a little later. All right. So that's basically what an offer is. That's how it's represented. So let's move on. One thing I guess I talked about earlier, it's not really, I guess I already went over all this, but the offer can be denominated in any currency, but eventually the invoice will be only in Bitcoin. So let's continue. All right. So now that Bob has given Alice an offer, or she obtained it somehow, Alice now wants to request an invoice so she could pay Bob. And so she constructs some message called an invoice request. And the way she sends this to Bob is she takes typically the blinded path in the offer, and she constructs something called an onion message. And this is something, as we dive deeper in, I'll explain a little more. And as the payload of that onion message would be the invoice request. And she's basically telling Bob, hey, give me back an invoice, and maybe here's some information I want in that invoice. As part of that, Alice would also include a blinded path back to her, which we call the reply path. And this allows Bob to send the invoice to her without actually knowing her node ID. Because before, the communication of the QR code or of the offer may have been through a QR code. So at that point, he may have no idea who Alice is, and he still wouldn't. All right. So let's go on and see. So this is the TLV stream, and so one thing you'll notice here is we repeat the offer in the invoice request TLV stream. And this allows for a few things. So it allows Bob, for instance, to not have to actually store the offer that he constructed. It's stateless in that sense. And that kind of ties back to the offer metadata. So Alice would also include the offer metadata as part of that TLV stream in her invoice request. And Bob would be able to sort of authenticate that that offer actually came from him, depending on how he constructs that metadata. Additionally, the payer, Alice, is including her own metadata in the invoice request. It's the first field there. Why it's the first one we'll get into in a little bit as well. And she could fill out a few things. So the chains there, if the chain is the mainnet, it just gets omitted basically. Like it's a way to save space in the QR code for the offer. So, but there could be multiple chains in that offer if there's like, I don't know, maybe on Liquid or something, they want to use BOLT12. So she could specify which chain she's paying through. The amount it could be omitted. So if the offer does not have an amount, there needs to be amount stated in the invoice request. If the amount or the offer does have an amount, it's either can be omitted by Alice when she constructs her invoice request, or if it's denominated in fiat, she may have to say, hey, this is the exchange rate, essentially. This is the amount of Bitcoin I'm requesting the invoice in. And at that point, Bob can verify that that's a reasonable rate before he issues the invoice. So that's why there's an amount field in the invoice request. For those two reasons, if you don't have an amount in the offer, or if the offer is fiat denominated. Similarly, there's the features bits for extensions. Quantity, so this is where Alice may say, hey, this is the number of items I want to purchase. For many invoices, that might be just blank and there's only one item. Then we have payer ID, which is kind of equivalent to the node ID or the signing key in the offer. And as you see at the very bottom, there's actually a signature here. So this is where Alice will sign the invoice request, and she signs it using that payer ID, which can also be transient as well. It's something that she could generate and something that she could rederive by including data including any information in the metadata, the payer metadata, in that field 0 or the record 0. There's a payer note, so she could add any information she wants to give to Bob. Paths there is actually not relevant for invoice requests, but for something called refunds, which we'll get into later. And then, of course, the signature that I just mentioned. And we'll get into how that is constructed as well. It's also a Schnorr signature. So that has some great properties for anyone that wants to do like a multi-sig for signing their invoices, or invoice requests for that matter. All right. And on the right side, you see an instance of this particular invoice request. I guess their green fields are from the offer. The blue one, we have some metadata on top, and then a few later on. So I can't quite read it from this angle, but I think what I had in here is Alice actually overpaid. She gave a little bit more, and that's perfectly fine if Bob wants to accept that. And she left a message saying, keep the sats, so I'll keep the change, basically. Yeah, so at this point, Bob is being sent an invoice request, so he can not even send an invoice back if he doesn't want to. Onion messages are unreliable, so Alice may have to, request an invoice until she gets one, or Bob could send an invoice error back. And I didn't add those in the slide, but there's an invoice error message as well that he could use to send back and say, hey, I don't like this request for whatever reason, and there's some information he could fill out. Yes? There's nothing in the spec about that. No, there's a field that says like this particular TLV record in your invoice request is invalid for whatever reason, and here's a suggestion of what it should be. So maybe it's for an exchange rate, for instance. Yeah. Yeah. So we'll get into onion messages in a bit. Like you think of onion messages as a layer in the abstraction where offers is just one use case of onion messages. So the invoice error is particular to offers, but other protocols built on top of onion messages could also define their own manner of error codes. All right, let's continue on. Okay, so we're moving along now, and now Bob likes the invoice request that Alice sent him, and he sends her an invoice back on the reply path that Alice gave an invoice request on your message. And in that invoice, he included some more blinded paths, and this will contain some more information for making a payment. And I kind of completed the flow here where Alice sends the Bitcoin to Bob using those blinded paths. So let's jump into the invoice now. So very similar to the last time, we include both the offer and now I guess the invoice request TLV stream in there. And in any additional invoice fields or records. And we don't include the signature from the invoice request, but we do include the signature of the invoice. Yeah. No, so this is a BOLT12. It's a BOLT12 invoice that's a new format. So yeah, that's this like the whole TLV record, TLV stream idea is quite different from BOLT11. So it is a new invoice format. All right, so we have our invoice. It has those blinded paths as I mentioned, and this blinded pay info that it gives some more information of how to make the payment. Like there's like CLTV expiries. And whatnot in there, I think like fee rates, etc. This is for the blinded portion of the payment. So, and we'll get into that in a little bit. There's some, creation expiration times. The payment hash, okay, so in BOLT11 we had a payment hash, and now we finally have our payment hash here. And the reason why, a BOLT11 invoice wasn't reusable is because of that payment hash there. And now, so an invoice here is not reusable as well. It's just that we have the offer as the precursor to it. There's the amount there. So this is the amount that Bob expects to be paid. And there's fallback addresses. So these are on-chain addresses in case, for whatever reason, Alice can't make the payment. Bob can offer other ways to pay. Those are optional, of course. Feature bits for extension. And then the node ID here is also a signing pub key, and it should either match the one in the offer, or it may match, which is a new spec change, a blinded node ID of one of the blinded paths. So there's a way to essentially verify that way, or sign that way, I guess, and verify the authenticity. All right. So let's get into blinded paths. So I'm not going to get into like the nitty gritty of like the cryptography around this, but kind of describe what it is and how it's used. So this is a key part of BOLT12. It offers like a tremendous amount of privacy for the recipient and also I guess for the sender, because if you're sending an invoice request, the reply path is using these blinded paths as well. So the blinded path is not a full path between Alice and Bob, right? It's just a partial path. And so when Bob constructs an offer, he includes a blinded path with maybe 2 or 3 hops to him. So in the world of BOLT12 in Lightning, typically you think of like the sender is forming the path, right? Like that still happens in BOLT12, but for the blinded portion, that's constructed by the recipient of either the message or the payment. So in our example, Bob would construct a blinded path to himself, maybe a few hops away, and make sure there's like, a reasonable amount of like possibilities that he could have chosen so that someone can infer, where he is in the network essentially. And of course, Bob might not even be an announced node, and blinded paths in that case are kind of necessary. Where in BOLT11, you're revealing your node ID in the route hints. All right, and so this particular example shows 3 hops where the last one's the recipient, so that would be Bob. There are 2 other nodes on this path where the first one is we call the introduction node. And that one it has to be a public node, so it has to be announced. And of course, it has to support route blinding. But what would happen is Alice would essentially route her message or her payment to that introduction node and then kind of tack on the rest as part of the path that she's sending the message or payment to. And then, as with any sort of onion routing, the person who receives the message or who is handling a message on one of the hops along the way knows who gave it to them and where it goes to, but that's all they know. And so we're essentially extending onion payments to work with messaging instead of payments. There's trade-offs there, of course. Like so, in onion payments, there's liquidity issues, right? You have to have enough liquidity to send a payment through a channel. With onion messages, you don't actually even need a channel if you knew that 2 peers were connected in the network graph. And there's no sort of like round trip, like there's no like signing dance happening between each of the adjacent peers, and there's not like an out and back, right? When you're doing the failing, because those onion messages are unreliable. It's either it gets there or it doesn't, and you don't know until you get a response, or you retry, I suppose. Of course, that kind of brings up issues like, can you potentially DOS the network by sending a lot of onion messages? So there's ways to mitigate that. Some of them aren't quite implemented yet, but given how young this network is right now, and the prevalence of support for onion messages, like it's not really a problem, but there's mechanism like kind of like back pressure to say, okay, you're sending me too many onion messages that could kind of propagate back to kind of where you find where the problem is. So those are, I guess, areas of research that have been looked at, but it still need to be implemented, is my understanding. All right, so for sake of time, I'm gonna keep moving along. So here's that example I was saying. So we have Bob, he's kind of at the right side of the network. Alice wants to send either onion message or a payment to him using that blinded path there. It's highlighted in blue. So Alice routes to the first node there. So it's, I can't read it, it's A, B, E, I, and then so forth along the path. So like I mentioned earlier, when a node is handling an onion message, it knows where it came from because they just delivered it to them, and it knows where to go next, but it doesn't know where it is along the path. So this, this is important for privacy, of course. All right, a time check. I think I'm got at least 15 minutes, so I'm going to keep going. So we talked about metadata earlier, and so both the recipient and the payer have opportunities to include metadata in the offer or the invoice request, and this is a kind of useful way to make the implementation stateless. So I'm going to kind of run through some examples of how that would be, and there's a few different varieties of how you may construct your metadata, of course, and different implementations of BOLT12 may do it in different ways. So here's one. So one way is that let's say you're Bob and you're creating an offer, and you the first thing you do is you generate a nonce, so a number it's only used once, it's kind of random, And from that, you compute an HMAC using some secret key material that only Bob knows over that nonce and all the TLV records in your offer, except for the signing pub key, which we're going to leave out for now, and the metadata, since we're constructing the metadata. From that, we take the HMAC and we use it to derive a key pair. And the public key of that key pair would be the signing pub key. So in this construction, only that purple box in the middle, that 16 byte or 128-bit nonce is included in the metadata. So your metadata would just be 16 bytes. When that offer is given to Bob or given to Alice, and she sends invoice request with that metadata back to Bob, Bob could look at that metadata and say, hey, is this an offer that I created? And the way he would do that is he would take the TLV records from the offer portion of the TLV records in that request, and he would essentially recompute that HMAC using the nonce in there and the records, and then recompute the key pair, and then just check, hey, does the public key match the signing pub key that was in the offer that was given back to me? And that's a way to do a pretty straightforward way of saying, like, you could, both have a derived signing pub key that's only used once based on that nonce, and to verify it statelessly. So that's like a neat way of doing it. Some people may not want to derive a key this manner. They might want to include their own key pair. In that case, what they would do is they would take that HMAC and also include it in the metadata. So you'll have the purple and the red box there. And so now they could just basically take, in the construction of that the HMAC would include their signing pub key, whereas before it did not. And then from that, they could, again, verify that the HMAC could be reconstructed and verify, I guess, in a sense that that offer was indeed theirs. So another way to have the stateless offers. And then the last part of this diagram I want to point out is that for a recipient of a offer, or sorry, the person who constructed the offer, those could be stateless. But for someone paying an offer, you may want to contain some state in your invoice request. So for the payer metadata, you would use the same construction, only you could include some payer ID. And thus you could kind of keep track of, like, hey, did I already pay this invoice? Or this invoice request. So I sent an invoice request. If Bob sends an invoice back to Alice, how does she know she's already paid it or not? Because he could send an invoice with a new payment hash each time, right? So if he does that, Alice has this payment ID in her metadata, she could then keep track of, like, oh no, I've already received an invoice. I'm about to send a payment. I'm just going to ignore this other one. So that's a way for we're adding, I guess, 32 bytes to the metadata in that case. But that's sent over the wire, right? That's on the Lightning Network. It's not in a QR code, so the size isn't too important there. There may be other ways to construct, like, your metadata. I think Core Lightning might do a different way with some tweak, but I'm not positive about that. But this is one mechanism. All right, any questions on that? That's probably the more technical part of this. Yep. Mm-hmm. That's true, yeah. Yeah. And so we wanted to provide a mechanism that is better suited for actually communicating, that doesn't involve the whole HTLC. Yeah, the dance, the locking up liquidity and whatnot. Stuff like that. So money messages are incredibly cheap, and we're talking about mechanisms that we can even make it cheaper by storing less information. Mm-hmm. Yeah, that's a good point. Perfect. I have a follow-up. Yeah. Could you clarify that a little? Like, oh yeah, I mean, if you make an invoice request, you'll get an invoice back or an invoice error. You, no, but I think it's cheap to create one. I don't know if it's too problematic. Like, so for inbound payments, at least in the LDK implementation, I think in others, any sort of inbound payment is stateless. So we're able to reconstruct any data we need, like the pre-image to the payment hash, using data that we include in like the blinded path, for instance, like, or the payment secret in the sense of BOLT12. So we're not too concerned about that. I don't know if that answers your question, but. It's still available, I gotcha. I'd say, like, since onion messages are unreliable, you might not get a response. There's no definitive way of saying, yes, it's still there. That said, there is an expiration, an absolute expiry in the offer. So if that has passed, then you know it's not going to be available. But yeah, but it's up to them to determine if. But yeah, but I mean, it's true that they may just not respond with an invoice. There's nothing getting around that. So if the offer is still, it hasn't expired, they may just not respond.
Is that just receiving the package is enough to verify, yes, this is an offer I created, yes, this is an invoice request that I received and I replied to, and then the payment matches the whole chain, right? So this is a mechanism for you to not have to remember about what you gave out as offers. Okay, thanks.
Okay. All right, we have a few more minutes so we can continue. So. Next, I want to jump into how a invoice request and an invoice is signed in BOLT12. So we have this concept of a Merkle tree in Bitcoin, and I think many people are familiar with that. In BOLT12, we are essentially constructing something to sign, a hash, and we're doing it in a particular manner for a variety of reasons. So I'm going to walk through like how it's done first, and kind of hopefully explain some of the rationale along the way. So this is a very small example, but you can imagine there's going to be a much larger tree. The top level are the leaves of the tree. L1, L2, and L3 represent TLV records in either the invoice request or the invoice. I'm just going to say invoice from now on to make it easier to say. And so that includes the entire TLV stream, including from the offer and the invoice request. And the interspersed items there, elements there, are nonces particular to each of those TLV records. And essentially, those represent a hash. So we'll go into how those were actually hashed. And from the top down, we're essentially saying, like, as you are moving down each level, we're having the amount of data that's hashed. So, for instance, when L1 and L1 nonce are combined, they're concatenated in a certain manner and then hashed using this tagged hash algorithm. And then the same thing happens with L2 and L2 nonce and L3 and L3 nonce. Then we're essentially left with those three blue items there, and these are essentially branches of the tree. And that continues on until, so there's an odd number there, so we're just kind of percolating the last one down one level since there's an odd number. But eventually we'll get to a root, and we'll hash that again using a tagged hash algorithm so that the message that we're assigning is specific to the context. So if anyone was in the, I think it was in the op-cat talk earlier, the cat VM talk, there was more details on how those are done. But that you could get into, like, I think it's 340 or 41 describes it. And then BOLT12 describes the exact algorithm, which the next slide will go into a little bit more information on. So this is by no means complete, but you can see some ellipses there on the slide. So the top level, there's essentially two hashing functions there. There's one for the leaf in the red on the left and one for the leaf nonce. The nonce one includes, as part of the, not the data that's being hashed, but part of the, I guess it would be part of the tag, I believe, is the first TLV record. And that, for anything that's signed, invoice request or invoice, is the payer metadata. So this is providing like payer-specific entropy to the signed message. And then we're including as part of that nonce, just the record type, which is I there. And then the leaf is somewhat similarly constructed, but we're using the entire TLV record and hashing that, and we get L1 and L1 nonce there. So, and then for the next level down, we're taking those outputs, we're putting them into our tagged hash algorithm for the branch, and it will order the items L1 and L1 nonce based on whichever's the smaller goes first. So it's comparing lexicographically, I believe, the hashes. So the order may switch as you're kind of constructing this tree. And that goes on until eventually you're down to just the root. And then there's, of course, the hash for the context. So it would be like Lightning invoice or Lightning invoice request. So there's more sort of details of, like, I think it's like a double SHA-256 hash, I believe. I'd have to look that up in the spec. But it kind of describes this. And so some, like, I guess, reasons maybe why we do this sort of like Merkle tree here is like, we can selectively sort of, like, if you sign a message, you could eventually like selectively reveal parts of what you signed using this construction. And by having a nonce next to the TLV record, you're preventing from, I guess, like exposing the adjacent record, I believe is the reason for that. All right, I got only a couple more minutes, so I'm gonna have to keep moving. There's refunds inside of BOLT12 as well. So a refund is essentially an offer without an invoice request, or it's an offer for money. So if you pay an offer and you want to return the item, for instance, you may want a refund for that item. So in this case, we have the same example with Bob having the offer before. Now he may be refunding the money to Alice, and so he would present a refund, which is essentially some offer records and some invoice request records, but as a QR code. And it won't be signed, just like an offer wasn't signed. And now Alice would directly send an invoice to Bob using any blinded paths that are inside that refund, and then eventually it would be paid. So there's just kind of like one step is removed from that.
Would that link to the previous invoice request? Like, I am requesting a refund for this invoice?
I think there's like a to-do in the spec about that, but that's, I think, is the reason to kind of have this similar construction with the streams, but I don't think it's fully implemented from what I remember. And I didn't put all the information in there about it, but the only difference is here is it's L and R instead of L and O. So R for refund or R for request, if you will. All right, so that's essentially like a lot of the details of BOLT12. There's probably a lot more I could have dived into, but for sake of time, I didn't really have an opportunity. I'm looking at some future-facing items. So I mentioned, human readable names. There's a proposal by Matt Corello for human readable names over DNS, and it also offers sort of an upgrade path from a world where you have like BOLT12 and BOLT11 or LN URL. Again, don't have the time to go into it, but there are some proposals out there right now, some pull requests for us in the spec. Async payments. So that's a big usability concern in Lightning now is like if the receiver is not online, they cannot receive their payment. So a way of doing this is being proposed by someone on my team, Valentine Wallace, and there's ways to do that without holding the HTLC and causing liquidity concerns on the network. So look at that for more information. And then lastly, payment notifications. This is pretty early on. I wrote a design doc based on some feedback from some companies that would like to essentially act as a point of sale in the BOLT12 world. So imagine a merchant has a Lightning wallet, but they want to have all their inventory and all their invoicing, or not maybe invoicing, but like all their orders sort of handled by a third party, whether it's like ZapRight or Cash App, or not Cash App, sorry, like by Block, for Square. They may want to have a mechanism for the point of sale to show an offer, but have the invoice request and the invoice go to the merchant's wallet, and have the point of sale be notified of a completed payment. And what the order or the offer, if you will, it's going to be a one-time generated offer in that case, so they could sort of update all the bookkeeping for them. So that's still in the works, but hopefully this year we'll have a more solid proposal.
Is that just sending messages?
There will be onion messaging involved, but there's like some sort of there's got to be a mechanism to do that where like essentially both the merchant or the consumer can say like, here's proof of payment essentially, because we don't want to remove proof of payment from the customer. I didn't really talk much about proof of payment, unfortunately, in the talk, but a proof of payment is essentially the invoice and the pre-image to the invoice. So you have something similar in BOLT12, only it offers as well proof of payer, so you could prove who paid, for instance, and that's done because the invoice will contain the payer ID as well. All right. So adoption hopefully could begin now. I guess I don't have much time to go through this, but I want to jump to this slide, I believe. So ideally, like you kind of just implement BOLT12, both paying and receiving. But if you could at least pay BOLT12 first, that would be ideal, or at least be the second best, I guess. And then the same with human readable names for this upgrade path. And then finally, of course, receiving as well. And then receiving from a human readable name, because you could then support other mechanisms of receiving, like LNURL, and have this upgrade path to BOLT12 in the future. So, and then later you could always implement BOLT12 receive. But hopefully, with implementations kind of rolling out BOLT12 now, like this is going to become like something that's consistent, or is going to be starting to be rolled out on the network. So LDK is the project I work on, and we have an implementation out. Core Lightning has an implementation as well. Async I guess Eclair has their implementation. And then I had a previous slide here, but there's something called LNDK, which is essentially another process you could run alongside LND to include support for offers. And I believe the LND team is actually working on offers as well, so they'll have full support, hopefully, I think in like 2 releases I heard, but we'll see how that goes. So 2 weeks or 2 releases. So with that, thank you. Any questions? All right, so one back there.
Early on in the presentation, you talked about recurring payments denominated in like fiat or USD.
Yep.
And my question is, what is that negotiated between the sender and receiver on like the order pool of what determines that conversion? And then the follow-up there is, does the offer during that entire time stay static with fluctuation, or does the offer need to also be updated?
So the offer would be denominated in fiat in that case, in this example, I guess. And the offer expiration time allows you to change, or if you have a shorter expiration, for instance, you could just create a new offer. But as far as the foreign exchange rates, having this oracle, as you mentioned, essentially the invoice request is sent out either with or without an amount. So let's look at the one example. Like an offer is denominated in USD, and Al sends Bob an invoice request that's blank amount. She's relying on Bob to send an invoice back that's converted to MSATs, and she could decide whether or not she pays that based on the exchange rate. Alternatively, she could propose her own exchange rate, put that in the invoice request, and when Bob looks at the invoice request, could say, hey, this is too small, or and say, hey, no, I'm not going to send an invoice back. I'll send an invoice error back instead.
Hypothetically, there could be some negotiation that happens
There could potentially be.
on what the price conversion is.
There potentially could be, I suppose, because like the invoice error could say this is why because it could say this is the amount I want actually, and I don't know if there's nothing specified about how the negotiation happens, but you could imagine that that's a possibility, I suppose.
But the offer stays static during that time.
Yeah, exactly.
Uh,
Yeah, you're good with the mic.
oh, so has anybody started using these for zaps? Because I feel like you could put a BOLT12 offer on a Nostr profile, and I feel like zaps are sort of a first killer. app
Ideally,
for
like,
BOLT12.
that would be a great use case. So if anyone in the hackathon wants to start this, that would be a nice project.
Noted.
All right, we have how many more questions? At least one in the back and one over here. I think we'll hear first.
Please.
Oh, he's asked a lot of questions. I'll let you go first. So there is MPP. Oh yeah. So for those in here, there's the question about atomic split payments. You said so. There is MPP in BOLT12, so multi-part payment. But I think I heard described somewhere else that you could potentially have multiple payers essentially pay an invoice, right? Each one paying a part, and eventually that being. Oh, multiple receivers. It's kind of is it Rainbow, or there's like a Prism? That's what it is, right? Yeah. I don't know if anything prevents it, but I'm not as familiar enough with that protocol to know if it could be emulated on BOLT12.
Well, I don't think those are necessarily atomic.
You could do like a wrapped BOLT12 and like get the same payment hash from everyone.
The only way you can do this with BOLT11s is if you make sure you're on the path to the
Yeah.
you gather.
Yeah, with blinded paths, like I guess maybe you could do something like that. Like, are you thinking like each hop on the blinded path potentially would have like one of the recipients essentially, and they would?
Or like completely split.
Yeah.
From the receiver or from the sender to two receivers, and somehow that is.
Yeah, it's a good question. I don't have a good answer to it honestly, but it's something that's good to think about.
All right. So somewhere in the midst of all this, you teased the concept of one of these TLVs, the type, I don't remember what you called it, a network or a
There's a chain hash.
So
chain
right.
hash,
So you
yeah.
could support side chains. Can you expand a little bit more on that, or perhaps
So
maybe
right now,
point us at a resource, online that talks about? For instance, I would love to see, as you said, Liquid being the obvious example.
Yeah.
And I would eventually like to see a whole mesh of elements-based
Mm-hmm.
side chains that can route payments like this. So.
Yeah, so the support comes at the offer level. So there's not just one chain, but multiple chains you could include there. And that's just a 32-byte chain hash, basically. So someone like Bob may say, I support mainnet, I support Liquid, and whatever other side chains potentially. And the person paying, an invoice request would put which chain they want to pay on. And since Bob said he supported that in LSN, say for Liquid, then he would expect that, or she would expect the invoice coming back would be specific to Liquid. And I guess maybe it's very Bitcoin specific in the sense that, I guess.
Sure.
I guess the spec does describe it as the amount being based on the network, so maybe not.
And it would allow for perhaps a list of them, so that
there is
client
allowed
could pick among the list and pick whichever one they already had the liquidity on or the best connection.
Yeah,
to
so
or
the
whatever.
offer allows a list, but once, the invoice request is only one, so you specify which one you want to pay on. Right, any other questions? All right, thanks for attending, everyone. Appreciate it.